ODPs to do over breath. All right, questions? Yes?
Do we have a final exam due date?
It's been on Canvas since before the quarter started. Should be. Or check Clark's.
I think I saw it on Canvas. It was either Monday or Wednesday.
Yes. So daytime final exam schedule. I just Googled Clark College exam schedule. So for winter 2019, what is this? This is an 11 o'clock daily, so it should be on Wednesday, March 20th.
Nice.
Yeah. And if you really want to come to the Monday one at 10 o'clock, you can do that. But you might be standing. But we can find more chairs. We can find more tables. So if that really works better for you, you can come to either section. Don't come to both. Don't come to neither. It's an exclusive or. How's the ODP?
Well, I finished yesterday, so.
Cool.
It's good.
Good.
Yeah.
Did it make sense?
Yeah.
Awesome. Cool. So my suggestion, if you're struggling with this, right, get your worksheet with your tries on it, or make a sample try on paper, and put down the algorithm you're trying to do in your find word function, and then run the algorithm, put some words in your try, like we did in class, and then run your algorithm against that, and see if it's doing the right thing. And mostly what you want is a temporary trinode pointer. Right, temp, for example, starts off at the root. Take the first letter of your word, look at temp, arrow, letters, bracket, whatever index corresponds to that, so the character minus an A, right? If that's null, just return a 0. And if the pointer's not pointing to a node, your word is not in the structure. You can return a 0 right there. Otherwise, have temp point to whatever that is pointing at. That's the second node in your try. Move to the second letter of your word, look at the corresponding pointer, temp, arrow, letters, bracket, whatever that index is. Set temp equal to that. If that's null, return a 0. Otherwise, move to the third letter, look at temp, arrow, letters, and keep going until you get to the end of your string. At the end of your string, temp should be pointing to a try node that has end of string set to 1. So if temp is null, return a 0. If temp, arrow, EOS is 0, return a 0. If temp EOS is 1, then you can return a 1 and say the words in my structure. But sketch that out in an algorithm and then run it against the paper and make sure that it's going down the right number of steps using the right end condition and so on. Alright, so I won't post more ODPs until next week probably. But I think you have till 5 today for this one. All right, any questions on sorting so far? All right, so let's, well, let me tell you what I told the other class. I'll tell you where we're going the rest of the term, because we got 3 weeks left. So next week you're still working on PA4, okay, trees, and we're going to be talking mostly about sorting. So today we're going to talk about Mergesort. We'll talk about Radix Sort. And next week we'll talk about something called Quicksort. And maybe topological sort. And heaps and heap sort. And that'll give us a pretty good collection of sorts. And then we're going to talk about dynamic programming. And dynamic programming is a tool we can use, particularly with recursive code, to speed it up. And PA5 is going to be a programming assignment that uses dynamic programming. And we'll look at a series of problems in dynamic programming, problems that if we just sort of go after it with a brute force attempt, take a really, really long time, even for small problems. And we'll look at some small problems, we'll write some code, and we'll see that it's like not going to finish in our lifetime. But with dynamic programming, we can make these things run really fast. So we'll play around with that. That'll take us into PA5. PA5 is a group project, so you're going to work in groups of 3 or fewer to get PA5 done. And then we're going to revisit tree balancing. So after PA4 has been turned in, we'll go back and we'll look at balancing AVL trees. We'll look at code for doing those rotations and stuff. And we'll talk about red-black trees, different approach to balancing. The last week after you turn in PA5, which I think is due on a Monday, you'll come up as groups and present your projects to the class, just like we did in 224. So we'll have a few days of presentations, a few days for wrap-up at the end. So week 10 will probably be presentations and review, talking about the final, and then we're done until 223. So this will probably be the rest of the quarter. So let's talk about merge sort.
I have a question.
Yeah.
So we need to do the presentation for the PA5 or the
Mhm.
project?
PA5.
Okay.
Yeah. Project presentations are still that last Tuesday of the quarter in the digital lounge 3 to 5. That's separate.
The PA5 has presentations.
Say what?
You said the PA5 has
Yeah, PA5 you present to the class after you turn it in.
That's a group, right? What you said?
Say again?
And that was a group thing, you said?
You can do PA5 in groups of 3 people or 2 people, or you can do it alone. All right, let's talk about merge sort. So, after a few years of teaching this course, it occurred to me to wonder how I alphabetize papers and what kind of sorting algorithm I use. So let's say that these are your midterms. And first thing I do is I alphabetize them. So here's the stack that I just got that everybody turned in. Here's what I seem to do. I take the first one and I put that over here. I take the second one and I put it before or after this one so that it's alphabetical. So I'll put that behind. I'll take the next exam and I'll say, okay, it comes after that. It goes right there. Take the next exam. That's nice. It goes right on top. I'll take this one. That's end of the alphabet, so that goes in the back, right, and so on. So what kind of sort am I doing?
Insertion.
That's an insertion sort, right? I'm taking from the input just by pulling the top paper off the stack, but then I'm choosing where to put it in my output pile so that my output is always sorted. So that's an insertion sort. Now if I get someone whose name starts with A, goes right on top of the pile, that's easy. If I get someone whose name starts with a Z, that's pretty easy because I know how many people I have. Well, actually, there's a lot of W's in this course. But if I get something with a Z, right, that's pretty safe bet. I can go straight to the end of the pile. If I get someone whose name starts with an M, I really don't know kind of where they go in the pile. It's kind of the middle. So I kind of have to start going through, paper by paper until I get to something that's too big, and then I say, okay, it goes right there. Okay, I got 60-some students. So after I've alphabetized the first 50 papers, I've got 50 papers in this stack. I pick up the next paper. On average, I have to compare it to 25 exams to figure out where to put it in here. And I got 10 of these to do that with. That's 250 papers I have to compare one another just to alphabetize the last 10. Okay, this is the price of an order n squared algorithm. So 60 students, it's a few thousand comparisons just to alphabetize your exams. This is why you don't get more exams, no. So I don't do a straight insertion sort. I run out of steam about halfway through that process. And it turns out then I switch to something called a merge sort. So let me show you what we can do with a merge sort. I take the first half of the papers, typically the ones from the morning section, and I insertion sort them so that they're sorted. And I put that over here. And then I take the second half of the papers and I insertion sort those. It's only about 30 papers each. So that's not too bad. Even n squared, it's less than 1,000. So now I've got 2 stacks of papers, 30 each, and they're each sorted, but I want to put them together into a single stack of 60 so that I can go through and enter the grades in Canvas, right? Okay, so I do this thing called interleaving, or mixing these 2 stacks. And it's really easy to do. I never have to rifle through the stacks of paper. I just select the top paper from one stack or the other. So here's what I do. I'm looking at 2 papers. I take whichever one comes first, and I put that in my output. And now I look at the top 2 papers. I take whichever one comes first. I put that in my output. Look at the top 2. Take the one that comes first. Put that in. Look at the top 2. Take the one that comes first. And I just keep doing this. So 6 and 8, 6 comes first. 7 and 8, 7 comes first. 8 and 10, 8 comes first. 9 and 10, 10 and 11, 10 comes first. And then when I get to a point where there's nothing in one of the stacks, I can just take this whole stack and put that on my output. And when I'm done, everything is sorted. So that gives us an idea for how to do an efficient sort. Efficient meaning doesn't take me too much time. So here's a merge sort. So I'm going to go heavy on pseudocode here because the details of actually making this work in C are kind of nightmarish. There's all kinds of weird little cases you got to take care of. And I'm just going to brush over those right now because I'm just going to write pseudocode. So I'm doing a merge sort on some array of numbers that I'm just calling data. And forget that in C we don't know how big that array is. We have to pass the size and all this kind of stuff. This is all just kind of algorithmic level pseudocode. Okay, so how do I merge sort my array of data? I'm going to sort the first half into an array called A. I'm going to sort the second half into an array called B. And then I'm going to say interleave A and B into our output. It's a really simple process. It's 3 steps. So we'll start with a fresh set of papers. Okay, I'm going to split this roughly in half. I'm going to sort the first half in some way. I'm going to sort the second half in some way. And then I'm going to do that interleaving process. Now the interleaving is really efficient. It's order n, right? Because all I got to do is go through all the n cards, and at each step I just pick the smallest of the 2 cards, copy that to my output. So this interleave is order n. But there's a detail I've skipped over, which is I have to take the 2 halves of my original set of data and sort them. So how should I do that? Should I do an insertion sort? That's what I do. But what would be the least amount of coding?
Merge sort.
Merge sort.
Yeah.
All right, so we'll just do a merge sort. Because, hey, we already got this great merge sort program that we just wrote. So let's just use that. Okay, classic recursion. So anytime we have recursion, what's the one thing we got to make sure we got covered?
Case for an empty stack.
Yeah, some kind of base case to get us out of this recursion. Otherwise, we're just going to keep calling merge sort again and again and again. We're going to blow up our stack. So we need some kind of way to get out of this. What comes to mind? What's a good way to get out of this?
One stack has to be empty, then we put the other stack on top of the output.
We could do that. Let's do something even lazier.
It's only got one item, it's sorted.
Yeah, let's do that. If data has only one number, just copy to output and return. So if we're asked to merge sort a set of data that consists of only a single number, we don't have to do anything. We definitely don't need to call any recursion. We can just say, hey, your number's already sorted. Your list is already sorted. Just copy it to the output and return. Otherwise, split your data into two halves, merge sort each of those halves, interleave them, and then return that interleaved result. So this is a class of algorithm that we can call divide and conquer. And a lot of algorithms fall into this category. Divide and conquer basically says we have some problem we want to solve. We're going to break that into some smaller problems, solve those, and then put those solutions together to get our solution to the original problem. So it's taking a big problem, cutting it into smaller pieces, solving those smaller pieces, and then combining your solutions. And this is recursively divide and conquer, because the way we solve our smaller problems is by cutting those into even smaller problems. And we solve those by cutting them into smaller problems until we've cut it down to the place where our problem consists of sorting an array of one number. And there we just say, oh, it's already sorted, I'm done. And then we pop back up and we interleave everything, and it all just kind of works. So let's look at a merge sort. Now there's lots of details, right? If you have an odd number of things in your array, you can't split them directly in half. So you're going to have two halves that don't have exactly the same number of things. You got to deal with that in your code. Okay, when you're interleaving, if you run out of cards in one pile, you got to realize that, so you don't try to compare the top card of one pile to a non-existent card in the other pile. Right, so you have to deal with edge cases and so on. We're brushing all of that under the rug for now. So let's merge sort this array of 10 numbers. Well, we split it in half, and we say let's merge sort this, let's merge sort that, and then let's interleave. Okay, how do we merge sort this pile of numbers? Well, first we merge sort this, and then we merge sort this, and then we're going to interleave. Okay, how do we merge sort this? We split it into two arrays, 4 and a 2. We merge sort each of these, and then we interleave. Well, when we merge sort an array containing just the number 4, we get back a 4. When we merge sort a 2, we just get back a 2, and now we interleave, and interleaving says, okay, look at the first element in each of these, pick the smallest, that's a 2, that goes into our output, and then look at the top entry, there's only one on this pile, that's a 4, that's the next thing in our output. So that's the result of doing merge sort on this 2-element array. And now we do merge sort on this 860. So we split it in half. We get an 8 and we get a 60. So merge sort an 8, well, it's only got one element, so it's just going to give us an 8 right away. Merge sort is 60. It's just like we did up here. We'll split it into 2 arrays, one containing a 6, one containing a 0. We'll merge sort each of those, which will give us a 6 and a 0, and then we'll interleave. So we'll say, okay, take the 0 first, and then take the 6. So that's the result of merge sort on 60. This is the result of merge sort on 8. Okay, what's our algorithm? Merge sort the first half, merge sort the second half, and then interleave. So now we have to interleave this with that. So look at the first element in each and pick the smallest, that's a 0. Now look at the first element in each and pick the smallest, that's a 6. Now look at the first element in each, there's only an element here, that's an 8. So we get a 0, 6, 8. That's the result of doing merge sort on this. And this was the result of doing merge sort on that. So our step that we were working on was merge sorting this 5-element array. And how do we do that? Merge sort the first half, that gave us 2, 4. Merge sort the second half, that gave us 0, 6, 8. Now we have to interleave. So how do we interleave this with this? Look at the first element, pick the smallest, that's a 0. Look at the first element, 2 versus 6, that's a 2. Look at the first element, 4 versus 6, that's a 4. Look at the first element, well, it's nothing versus 6, so it's going to be 6, and then nothing versus 8 is going to be 8. And what have we done? We've done the first step of our original call to merge sort, which was merge sort the first half of our data, and we got 0, 2, 4, 6, 8. If we go through all of that again, we will end up merge sorting this set of data, which will give us 1, 3, 5, 7, 9. And then we'll interleave these, and we'll end up with a 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and we're done. All right, so if you're Transylvanian dancers, you do it like this. There's music here, but it doesn't play through the speakers. So imagine music.
Oh. And you should just sing to it.
I could sing to it and dance along. So first 2 elements, right? So first half of the list got split into 2 and 3. The first 2 just got interleaved, and they go back. And then we sort the second half, so split it into 2 pieces. Merge sort the 8, 8's alone, so it doesn't change anything. Merge sort the 6 and 0, so split them into 2 pieces. They're already sorted, so take them and interleave, and now you've got a 0, 6. And now we're going to interleave the 8 with the 0, 6. So compare the top entry in each, and take the smallest one, put it to the output. Compare the top entry in each, take the smallest, put it on the output, and last entry. So now we merge sort those elements 2 through 4. And now we're going to interleave the first 2 elements with the next 3 elements. So the 0 and 2 will compare to each other, and 0 will go to the output. And the 2 and the 6. And then there's nothing left in the first set to compare to, so the 6 will go out, and then the 8. And there's the first step of your 3-step merge sort. And then you got to do it with the second half. I don't know what the twirl is. Yay. It's probably freeing memory or something. So in the second half we'll do the same. And they're almost sorted. Right, and this was the point we were at here.
So many tutor that's actually more efficient than just.
Yeah. Alright, and there you go. We'll take it to the glorious end. And there's your merge sort. What? Yeah. So, we got to do Lego bubble sort too, because that's really fun. Stop action to the rescue.
Stop motion.
Stop motion. This is like so awesome in so many ways. We won't go through the whole thing, I just want to show you the first parts of it. So you start with the first element, compare it to the number after you. If you're out of order, you swap. I don't know how long it took to make this. I've done some similar things, but I don't think I had this much patience. Alright, so there's your first pass, and the tallest structure is at the end.
I like how he just teleports
I know.
across the top of the beams.
Yeah, pretty good at jumping. Right, so you always compare to the next entry. If you're out of order, you swap. Otherwise, if the next entry is largest, that becomes the number that you're going to consider, so you move to that one and compare to the one after, and so on. And after this pass, they should be have two of them in the correct spot. I don't know what happens at the end. I didn't make it that far. They're sitting down. So this is not an efficient bubble sort. Oh, there we go. All right, so merge sort. So order of complexity. Interleaving is order n. We don't really do anything here. We just call merge sort, which doesn't take any time. The edge case where you only have one number doesn't really take any time. So this whole merge sort is basically order n for just these steps. But the trick is it actually calls merge sort 2 times each time that you call merge sort. So yeah, the question is, how many times do we end up calling merge sort? Merge sort is order n, and n's getting smaller, but how many times do we actually recurse? So if you start with, yeah, so it's going to be logarithmic. So if you start with 64 numbers that you want to sort, you're going to call merge sort on 32 numbers twice. And to merge sort 32, you're going to call merge sort with 16 numbers. And to do merge sort on 16, you're going to do merge sort on 8. And I should have picked a smaller number. But this will go down until you call merge sort with 1. And this comes out looking like log n iterations, right? Because we're dividing in half each time. How many times do you have to divide n elements in half till you get down to a single element? It's roughly log n. So this will work out to be n log n. And you have to do some work to get there, because even though you're calling roughly n merge sorts, the size of the thing you're sorting is getting smaller and smaller at each step. So it'll turn out to be n log n, which is nice, way better than a bubble sort or selection or insertion. So if n is a million, right, n squared is a trillion. It's a million million. N log n is approximately 20 million. So 20 million versus a million million, pretty significant. And sorting a billion pieces of data is not uncommon. Right, so 10 to the 18th versus 32 times 10 to the 9th. One is doable, the other is not. But financial data, fundamental data, stock market, things like that, a billion pieces of data is not unusual to work with. Credit card companies, trillions of pieces of data sometimes. So these differences between, say, n squared and n log n become pretty profound. So there's details if you try to code this that you have to pay attention to. For example, if your array has an odd number of elements, you got to choose where do I put the extra outlier. So you write code to deal with that. When you're interleaving your two arrays, you need to sort of keep track of where the next element in each array is. And if you get past the last element in one array, you've got to know that. So you don't try to compare a non-existent element to another one. So you've got lots of if statements and conditions like that. But fundamentally, it's a very straightforward algorithm. Never realized there were room numbers on the lights in here. I guess that's so somebody doesn't steal our lights and put them in another room. Okay, so next sort, Radix Sort. So a Radix Sort is cool if you have stuff that you're sorting that you can think of as character by character. So normally when we sort integers, we're comparing one integer to another using a compare operation in the CPU. But if we think of a number as just being a succession of digits, we can use a Radix sort. And we can also do this when we sort words. We can think of a word as a succession of characters. And if we can compare one character to another, a Radix sort is a nice candidate. And Radix Sort kind of looks like it's order n. It's really not, but it kind of looks like that. So let's put some numbers down. I don't know if that'll be a fun sort or not, but we'll just go with those numbers to begin with. All right, so here's a set of numbers. And they're all the same length. If I had a two-digit number, I'd put some zeros in the beginning, so they're all the same length. Okay, 3 digits in this case. And I'm going to think of this as digit 1, digit 2, digit 3. Okay, so we're going to make a total of 3 sweeps through this data, and when we're done, our data is going to be sorted. Okay, and here's what we're going to do. First, we're going to sort by digit D1. So we want to rearrange these things so that they're in sorted order according to this least significant digit. And we want to do it in a way that if we have two things that have the same digit, we don't rearrange them. This has to be a sort that doesn't disturb the order of things unless they have to be rearranged. So here's something with a 1, and here's something with a 1, and here's something with a 1. They need to end up in the same relative order in the output. Okay. And there's some versions of sorts that do that. Bubble sort does not do that. A selection sort will do that. It'll preserve that order. Bubble sort moves everything around along the way, right? But here's another way that we can do this. Since we know we only have 10 possible values for a digit, we could make 10 passes through this. And here's what we're going to do. We're going to make one pass, and we're going to look for anything that has a 0 in this rightmost position. And anything that has a 0, as we encounter it, we're going to add it to our output. So we'll go through here. There's a 300, so we'll put that in our output. And that was the only thing with a 0. We'll sweep through again. We'll look for anything that ends with a 1. So here's a 231. And here's a 131. And here's a 201. And that's it for the 1s. We'll go through and look for 2s. There's a 442. And that's it for the 2s. Look for 3s. There's no 3s. Look for the 4s. There's a 624. And there's a 154. Look for the 5s. There's a 525. And there won't be any 6s, 7s, 8s, or 9s. Okay, so this is our first of 3 steps. Okay, and the way I did it involved 10 passes through my data. But the result is my data is sorted by this digit D1. And now we're going to make a second pass, and we're going to sort by D2. So I'm going to look at the second digit. And again, I'm just going to do the same thing. I'm going to go through 10 times. I'm going to find all the things that have a 0. So 300, 201, that's it. Find all the things that have a 1, anything with a 2, 624, and 525. Anything with a 3, there's 231, 131. Anything with a 4, looks like 442. And anything with a 5, 154, and then no 6s, 7s, 8s, or 9s. All right, and then my third and final operation, sort by digit 3. So I'll look at this digit. So I'll go through and find any 0s, no, find any 1s, write them down in order, 131, 154. Find any 2s, there's 201, 231, that's it. Find any 3s, there's 300. Any 4s, there's 442. Any 5s, there's 525. Any 6s, there's 624. And there's no 7s, 8s, 9s, or 10s. And we're done, and guess what? Our data is sorted.
So they just call it gonna be array.
Yeah, you gotta figure out how to store these things and how to get the corresponding digits. So you could use an array, or you could use a string. String is going to be the easiest because you can just say bracket. It's basically an array, yeah. So how much work do we have to do to sort this original array of n numbers? Well, each one of these passes is basically n operations, right? We had to go through and we had to look for a particular digit in a particular place. We had to go through n numbers and see if this was a number we should copy to our output. And we had to do that a total of 10 times, looking for 0s, 1s, 2s, 3s, up through 9s. That let us complete one of these passes, and we had to do that, in this case, a total of 3 times for the first digit, the second digit, and the third digit. So we ended up doing 30 times n. And O of 30n is the same as O of n. So if we're only dealing with words that have, say, 10 letters or fewer, and we only have 26 letters that are legal, that sounds like O of 260 times n, which is order n. Doesn't matter how many words we have. You could have 1 billion words as long as they're 10 characters or fewer, and you only have 26 legal characters. It takes 260 times n operations. It's still order n. So at first glance, this looks like a really, really efficient sort, right? Because the best sort we're going to encounter is going to be n log n. That's merge sort, it's quick sort, it's heap sort. And this is only n. But it's a little bit of a lie. So if I give you a radix sort and I say we can sort n pieces of data in roughly n operations, somewhere your brain should go, well, can I do this with binary data? So let's try this with integers. Let's just think about sorting 32-bit integers. Let's stick with this. Let's not go binary yet. Suppose we have 32-bit integers. Well, what's the largest 32-bit integer?
255?
32 bits. That would be 8 bits. If you bought hard drives back in the 90s, you would know this, because there was a fundamental limit on hard drives because the file system was 32-bit based.
Is it around 65,000 or?
That would be 16. So roughly the square of that. So 2 to the 32, 2 to the 32 is approximately 4 billion. So 4 gigabytes. Which means as integers we can go plus or minus 2 billion roughly. So let's just forget about negatives. Let's just go positive integers. So roughly 4 billion. Okay, which is 10 digits. Okay, so that's what 4 billion would fit in. So we have roughly 10 digits to consider, and for each digit we have to find the zeros, 1, 2s, 3s, and so on up through the 10s. So 10 possibilities each. So it's roughly 100 times however many integers we're trying to sort. So radix sort on plain old 32-bit integers, roughly order of 100 times n. Well, suppose we have a merge sort, order of n log n. And n sounds better than n log n, right? Suppose we want to sort all integers. Suppose we take all 4 billion integers, we throw them in a huge array, and we want to sort them. So n is 2 to the 32 integers. Log of n is only 32. So a merge sort on 4 billion integers takes n times log n, which is 32, takes 32n operations. A radix sort is going to take 100n operations. It's going to take longer to do a radix sort. So even though asymptotically this looks like order n, the reality is, even if n is up to 4 billion, n log n is really only 32 times n operations. And that's better than this thing that looks like order n, right? So the constants can come into play. If something is order 10 gazillion n, chances are that might be worse than order n squared, right? If n is only 1,000,000, n squared is 1,000,000 squared. 10 gazillion n is 10 gazillion million, right? It's bigger. So it gets interesting if you think about doing this on your numbers represented as binary values, because we can write all of our integers as 32 digits, where each digit is either a 0 or a 1, and we can do a radix sort on that. And what do we have? Well, we have to make 2 passes through our data, looking for a 0 or a 1, and we have a total of 32 digits. So this is basically 64n. And if you're really good, right, and you're sorting into the right place, you really only need 1 pass, because after your first pass, everything that's left just moves into your output array. So a radix sort on a bunch of integers represented as binary, where you're working radix 2, you can really get that down to order 32n, and that's exactly what n log n would give you. So that's just kind of a weird analysis that these orders aren't always the final word on computational efficiency. Because we brush the factors under the rug and say asymptotically this is n, but the factors can make a difference in particular situations. All right, so Monday we will start talking about quick sort, possibly topological sort, definitely heaps and heap sort, and then we will move on to dynamic programming.
Ones that use like the memory locations instead of actual memory.
In what way?